First up in this part of the show, I'm going to break some boards. Got 5 3/4-inch pieces of pine. I don't know anything about karate, but if I apply a big force in a short amount of time and impulse, I should be able to break them. Hey, that was 3 3/4 inches of pine. Pretty good. Let's look at it in slow motion. Oh, looks like I really only broke one board at a time, and then the wave went through and broke them all. That looks pretty neat. Not quite as impressive, though. Let's try the dropped slinky. Take the slinky and let it stretch out, come to equilibrium, then let go at the top. Sure enough, it falls. But let's look at it in slow motion. The top's falling, but the bottom hasn't moved at all. It didn't know I let go of the top. It was held up by the spring force, and until the top part hit it, it stayed right there. Crack the whip. My son Samuel's going to do this demonstration. Sounded pretty good. So how do you crack a whip? The idea is to send a wave down the whip, and the wave's got to go faster than the speed of sound. If it does that, it'll emit a sonic boom. That's the crack. Well, Samuel's getting it ready to send that wave. Notice that the whip is thicker close to the handle and gets thinner and thinner. That's important. Here goes the wave. You notice it goes faster and faster as it gets thinner, and there's the crack. Perfect. Tuning forks. Let's have a little fun with them. Whack a tuning fork and make it vibrate. It makes a little sound. It's not very loud, especially with background music. But we can see it vibrate. Look at that one. Here's one that's a little shorter. It's going to vibrate at a higher frequency. I'm fairly disappointed that I can't really see it move. Something to do with the frame rate and the frequency that it's going at. But I think I can fix that. What I'm going to do is I'm going to slow it down, and then maybe we can see them both go. Yeah, look at that. So I slowed it way down, and now you can see them both vibrating. Get a tuning fork going, stick it in water, and look at it spray. Well, let's look at that in slow motion. Now I did that pretty fast, you saw in the video, but at 1,000 frames per second, it takes a long time to get to the water. Patience. Patience. Oh, I think it was worth it. Here's a giant tuning fork. This is called a choir chime. It's got a big tuning fork and a resonant chamber. Now let's watch it in slow motion. Kind of cool to see the striker. Oh, look at that thing vibrate. It's got a low frequency, so it vibrates slow. Wave on a string. Stretch a string out, drive it at the right frequency, you can get standing waves. There's the fundamental or first harmonic. There's the second harmonic. There, I got it good now. Third harmonic, fourth harmonic, fifth, and sixth. Not bad. Let's see that in slow motion. This is awesome. This is the third harmonic. Look at it go. Beautiful. Breaking a goblet with sound. Sounds fun. If you take a wine glass and tap on it, you get it to ring. That's a resonant frequency with this glass. If I was to take it, put it right next to a very powerful speaker like this one, tune that speaker so that it's the same frequency, I might be able to get it to break. I'm going to put it inside of this protective shield, and then we're going to give it a try. Here we go. Awesome. Now let's look at the slow motion video. The straw's there to show you if you're getting close to that resonant frequency. Look at that goblet. You can see the standing wave in it, vibrating pattern. If we can get that frequency just right, that's when it breaks. There it is. Look at that piece of glass sitting right on the speaker. That thing got sucked right over there. Now that speaker's driving in and out and in and out. I got to think about that one some more. There's a law in physics called entropy. It says that things tend to go from order to disorder. That's generally true unless you do a lot of work, or if you're doing a demo show like this. I think maybe we can violate that principle. Here we go. Look at those pieces of glass spinning around. And we got our goblet back. Well, that worked well. How about we unbreak some boards? All right, that was impressive. Next up, crushed can by induction. This coil is connected to a great big capacitor. I'm charging it up to about 5,500 volts, and then all of that charge will be dumped through that coil, and let's see what happens to the can.
5,000. Nearly 5,500.
It's collapsed. There's a current in the can that's in the opposite direction as the current in the coil. Opposite currents repel each other. Look at the high speed. Now this was filmed at nearly 3,000 frames per second, a lot higher frame rate than I've shown you before. Let's try another can.
Maximum voltage about 5,500.
Capacitor charged. Discharged. Let's look at the coil this time as it collapses. Did you see the windings are attracted to each other? That's because the current in them is going the same direction. Current in the same direction attracts. I framed this can at nearly 6,000 frames per second. You still only got a couple of frames of collapse. It's so fast. The vibrating light bulb. This has to do with current and magnetism. You've got a Edison style light bulb with a loose carbon filament. Bring up a magnet, it seems like it blurs right out. But in slow motion, you can see the filament is going back and forth, back and forth. It's that AC current. It's filling a force one way, then the other, one way and the other. Next up, magnet array. There's 48 magnets here, all north pole up. They're in equilibrium, but it's not a stable equilibrium. Drop a magnet in the middle, look at them go. We got to see that one in slow motion. Oh, look at them jump and spin. See that purple one doing somersaults? Not going to get all of them, but most of them. There goes the lone black one. You know, that white and black and purple one, it gets there eventually, but at this frame rate it took 20 seconds without hardly moving. So I cut that part out. Here it goes. Here's another chain reaction. 24 mouse traps, 48 ping pong balls, another unstable equilibrium. I'm going to set off one of the mouse traps, it's going to throw a ping pong ball, and then let's see what happens. Yeah, chain reaction. Let's look at it in slow motion. This can be used as a model for a fission chain reaction. Every time you have a fission event, it releases neutrons. Neutrons can lead to more fission events. Well, that's it for this part of the demo show. There's still one more video. Don't miss the finale.